So in this short section of 6.4, we're going to take a look at some properties of definite integrals. Again, definite means that we know the bounds, so we are definitely able to calculate the area under a curve. So rolling through these 8, I'm hoping that some of them are kind of common sense to us. Other ones we might have to think about a little bit more in depth for, but I think that these are going to go fairly well with these properties. So if we look at the first one, notice how we're going to try to figure out the area under the f of x graph, but our bounds are from a to a. So if we actually use the fundamental theorem of calculus to kind of see where this is going to guide us, we would first have to work backwards from f of x. So I'm just going to let g of x represent the antiderivative. Okay, if we were to work backwards, this is what we would get. So then we would throw in our bracket, rewrite our bounds, and according to the fundamental theorem of calculus, we plug in the top bound into the antiderivative, and then we subtract what we get when we plug in the bottom bound into the antiderivative. So if I plug in a, I'll get g of a, and then I have to subtract what I get when I plug in the bottom bound of a, which is also g of a. So if both of these are the same thing and we're subtracting them, notice how it makes sense that our area value would be 0. And if you think about the notation itself, this is telling us that we're starting our area calculation at A and we're also ending it at A. So you technically don't even have an interval because you're beginning and ending at the same point. So it makes sense that if we don't have an interval, we technically shouldn't have an area anyway. Okay, so if the bounds are the same, our area value will always be 0. Our second property tells us if we have a definite integral that goes from a to b, and there's some number in between a and b, in this case c, that we know, we can break up this entire interval into 2 separate ones. So for instance, if I let a be 1 and b be 5, maybe our c value would be 3. I can calculate the area from 1 to 3 and add that to the area from 3 to 5, and that should give me the total area from 1 to 5 in the end. So if we know something, a value in between the bounds, we can use that to break up the overall integral into maybe easier, smaller ones. Looking at 3, they're initially telling us that the area under the f of x curve from a to b is this value of k. Notice though how in the other integral they switched the bounds. So what this is actually doing is negating your area. So for instance, instead of going from 1 to 5, if we go from 5 to 1, we're technically working backwards. Okay, notice how we're starting at 5 and ending at 1. We're going backwards on the x-axis or backwards in time if we have that unit of measure with us. So the area is actually going to be negated. If you switch the bounds, you need to switch the area value. Okay, it becomes the opposite. B is kind of similar, 4 is kind of similar. They're telling us that B is the smaller number than A. So for instance, maybe I'll let B be 1. So this is telling us we're technically going from 5 to 1. Okay, and if that is working backwards, we're starting at 5 and ending at 1. Notice how I can negate the bounds, okay, negate the area, aka switch the bounds, and that's going to make my area negative. So 3 and 4 are very similar in the fact that if you switch the bounds, you have to negate or make your area negative. 5 I'm hoping is kind of self-explanatory or common sense to us. If we are multiplying a function by a constant, you can factor that constant out, very much like how we usually keep constants or coefficients when we take derivatives. You can keep those coefficients when you integrate something. So if you do have a common factor or a value, a coefficient, you can pull that out and use that later for your calculation. Okay, you don't have to actually go through the antiderivative with that in there. 6, I'm hoping, is another common sense one. If you are working backwards from multiple items, you can break those up and work backwards individually. So basically anything written before the dx on the end, remember that represents a change in x value, okay, a base width for our rectangles. Anything that's written before that, you have to work backwards from. So maybe we want to integrate each one individually instead of doing both of them at once. The last two kind of have a graphical representation for us to visualize this property. So we're going to first assume for 7 that f of x is an even function. Thinking back to pre-calc, we mentioned how that displays y-axis symmetry. So if you were to fold the graph from the left to the right and make the crease on the y-axis, the graph would match up. And notice how in this case we're going from a negative bound to a positive bound with the same numbered value. So for instance, -3 to +3. If that's the case, notice how we're going to have the same amount of area on the left as we do the right. So what we can do is maybe shorten the notation. Instead of going from -a to +a, I can go from 0 to a, so from here to here, and simply double that value because I know I have the same amount of area on the left. 8 is something similar, but this time we're looking at an odd function. So this is where you have that origin symmetry or 180-degree rotation. Basically saying if you flip the graph upside down, it should be exactly the same. So again, I'm going to take a look at the bounds from -a to +a, so same distance on the left and the right as we are from the origin. And looking at this, if I have origin symmetry, that means I have the same amount of area underneath the x-axis as I do above the x-axis. And we noticed how in a previous section that those two areas would actually cancel each other out, and we'll get an overall area of 0.